All right, there are a lot of ways to tackle this problem, but we're going to keep in mind the spirit of the note sheet that we're doing. We're looking at rational expressions and we're looking at reducing rational expressions. So we're going to tackle this problem by comparing a couple of rational expressions. So let's read it. Which jewelry box uses less material for the bottom and for the lid if the perimeters of the boxes are the same? A jewelry box shaped like a circle or a jewelry box shaped like a regular hexagon? All right. So if I'm shaped like a circle, I'm probably not talking about perimeter. I'm probably talking about circumference, but I think we know what they mean. We know that if a circle has a radius of r, the circumference of that circle can either be expressed as 2 pi r or as pi d, whichever is more expedient in that particular situation. Now, if a jewelry box is shaped with a base like a hexagon, we have something that looks like this. Now, a hexagon actually also has a radius, but it also has something called an apothem. The apothem is basically like the height of that little right triangle. It always goes to the middle of a base. Now, we don't actually have any numbers in this problem. The only thing we know is that the circumference of that circle is the same as the perimeter of this hexagon. So we know that C is equal to P. And we need a way to figure out which one is going to use less material. Well, using material, that's an area formulation. So the area of a circle would be pi r squared. Now the area of a hexagon, depending on what you've learned in the past, there's kind of two different approaches that you might take here. If you know the method of making this hexagon into 6 triangles, then you would say 6 times the area of one triangle. Okay, well, the area of one triangle, we know 1/2 base times height. Well, the base is S, the height is A, and we would be taking half of that. So that's really going to ultimately be 3 times the side times the apothem. Now, there's also a formula called apothem times perimeter divided by 2. This is the formula for the area of any regular hexagon. We know that the perimeter is 6s, so that gives us 6s times A divided by 2. And notice we're right back at 3sa. So whichever understanding you have of how to find the area of a regular hexagon, it reduces down to the same formula in the end. Now, here's the challenge. I've got an area formula for the circle, pi r squared. I've got an area formula for my hexagon, 3 times the side times the apothem. The problem is those are all different variables. I can't say which one would use more or less material with the current things laid out in front of me. But what I do know is that the circumference of that circle is equal to the perimeter of that hexagon. So as I think about that, I'm like, well, I need a way to describe them using the same variables. So if I look at this, I can say, well, if circumference is 2 pi r and perimeter is 6s, right? 6 times the side. How could I either solve for s or solve for r so that I can create expressions that are based on the same variables? Well, first of all, I could divide both sides by 2, right? Pi r is equal to 3s. So I basically have a choice. I can either divide both sides by 3, so I've solved for s, or I can divide both sides by pi so that I've solved for r. Personally, I think that's going to be a little bit easier, so that's the approach I'm going to take. The length of the radius is equal to 3 times the side of the hexagon divided by pi. I know that looks a little crazy, but now we have an expression that we can put in over here. So I've got the area of this circle is equal to pi times 3s pi all squared. Well, let's simplify this mess a little bit. I've got pi times 9s squared over pi squared. Well, the pi out here and the pi down in the denominator, that's going to reduce. So I'm going to have 9s squared over pi as the expression for the area of that circle. Now, over here on the right for the hexagon, I still have too many variables. The 3 and the s are fine because I've got an s in the other expression, but that a is an issue. I need a way to talk about the length of the apothem. So let's kind of do a little breakout here. If this is s, right, the length of the side is s, and this little height here is a, I can look at this little triangle down here. Well, think about your hexagons. I'm guessing that you know that one angle in a regular hexagon is 120 degrees, and that you also know that the radius breaks this into two equal parts. So those angles are 60. And all of a sudden you're like, oh, a 30, 60, 90 triangle. Okay, so we know that in a 30, 60, 90 triangle, across from the 30-degree angle, so this little part down here, if I double that, I get the length of the radius. So that actually has a radius that's the same length as one side of the hexagon. And the apothem would be the the square root of 3 times the short side. So the short side is half of the side of the hexagon, and that's times the square root of 3. So now I've got a way to describe the apothem in terms of s. So notice we've taken this myriad of variables and we've sort of all boiled it down to just using the length of the side of the hexagon as our only variable. So I'm going to come into this area equals 3 times the side times a, and instead of writing a, I'm going to have s root 3 over 2. So I've got to multiply that rational expression times this just monomial. So I've got 3s squared root 3 all over 2. That's a little bit of an awkward way to write that, but I'm down to something I can compare. I'm comparing 9s squared over pi. I want to know which is bigger, that or 3 root 3 s squared over 2. Well, you might notice there's an s squared in both of them. So actually the s squared doesn't matter. That's the same value. So really the question is 9 pi bigger or smaller than 3 root 3 over 2? Well, those are numerical expressions that you can type into a calculator and compare. Well, if you divide 9 by pi in your calculator, you're going to get approximately 2.86. If you take 3 root 3 over 2 and you type that into your calculator, you're going to get approximately 2.60. Well, we can see that the circle has the bigger area, which you probably guessed if you know anything about how areas of polygons versus circles works. So we can conclude that the container with the round base will have the greatest area and the hexagon will have the least area. So if we want to use less material, we're going to use the one with the regular hexagon.